Good morning, good afternoon, or wherever you are in the world. Welcome to today's panel discussion. Head and pillow, what causes it? How do you spot it? And how do you avoid it? Traditionally, head and pillow is one of the most difficult defects to detect. And this panel will look at some of the system's causes and cures. And I'm joined today by Piotr Swietoniowski from OMRON Corporation. I have Adam Murling from Indium Corporation, and we're joined by Kevin Martin from MacDermid Alpha. So welcome, gentlemen. Thank you for joining me today. I'm going to start actually with a question from that Piotr is going to start with. That is, how do we spot a head and pillow defect? So Piotr, you've got a couple of slides that you want to show us on the detection of these defects. Can you bring the first of these up, please?
Right. Thank you very much, Trevor. Basically, I just already introduced this is very interesting point in order if you are talking about how to spot it, how to inspect it. So basically, probably, especially if you are talking about some non-destructive tests, if you want to right now test it in mass production, 100% samples inspections, at the beginning in your process, for sure, you will recognize very quickly that the AOI is not capable to do it. And you will move directly to the X-ray inspection. But to be honest, actually right now, even most of the X-ray inspections machines that you have in the market, I would say are not capable enough to find a head and pillow defect. So,
okay, so what are we looking at here?
Okay, so basically here, just a very quick comparison between the different X-ray technologies, so popular technologies that you can use for inspect. Basically, in general, you can use for X-ray inspection. So here on the left side, you can see very traditional 2D inspection. So here you're just taking one simple shot from the top. This inspection is maybe quick, but its capability is very limited. So for the simple defects inspection might be okay. If you are talking about the head and pillow, this is for sure not enough. Another technology we call 2.5D. One of example is tomosynthesis. Here you are basically making images from just few fixed angles, and as a result, you can see just very limited slices of your object. So if you are very lucky and your surface of your PCB and your component didn't work, maybe you can find some defects. But the top capable technology, and in my opinion, the only technology that allows you to find head and pillow is a CT, so basically computer technology, computer tomography. So here we are just taking images 360 degrees around our measured object, and we are moving around our object 360 degrees around and just taking many images around. And based on those all images, we are reconstructing full volumetrical image. So here you have 100% information, what is happening in your measured object, and very detailed information about all defects and everything what is going on. On the right side of the screen, just a few images and just the X-ray images that are created using these technologies. So we can see two on the left, 2D and tomosynthesis. There maybe even if you see some defects, another thing, if you are talking about the mass production, we need to also create very stable programs. So here you need to have a very skilled programmer and probably even more skilled operators to find it in verification station. In computer tomography, situation is different. System will find correct slice automatically. So system is jumping between the slice and it's looking for correct level to analyze it and to find correct to find this head and pillow. When we are assembling in SMT, we can face, of course, PCB warpage or component warpage, and having this full volumetrical information of your component is giving you extreme good advantages, because most of the traditional X-ray systems, they're just cutting your component in one slice. So there's a very high chance that you will see your defect. And here in OMRON, our machine is using CT. We are taking every component individually, and inside this component, every VGA ball individually, and we are analyze every ball separately and finding correct slice to apply our logic to do it perfectly. So even if you have a warpage, it doesn't matter. It comes from PCB, comes from component. We are capable to eliminate this warpage in our inspection. Here's just an example how the example of image from the city, how it looks. So basically here we are just jumping through the slices from the bottom of the component. So you can see here is the middle of the ball, and we are going towards component body and here. So basically you can just spot wherever level you like, and there is not possible that any defect will be hidden from us. So this is, in my opinion, absolutely must, absolutely necessary in order to find head and pillow. But not only, if you want to find any other defects, any problem with the shape, or even voids, if you want to find it, it's of course very good if you can inspect complete volume than rather than just a single slice. Okay, just a very quick introduction about this X-ray technology. So
thank you for that, Piotr. I mean, Kevin, let's see. Is full CT the only way to detect head and pillow defects, or are there other methods out there?
I think from my standpoint, I guess obviously you can do destructive testing to see, right?
Right.
As far as a lot of X-ray techniques aren't always going to be have 100% capture. I think the presentation he just showed, he actually showed some things that were interesting to me, because I know, for example, traditional X-ray won't always catch it, and that's one of the bigger issues with head and pillow is having defects that slip through detection. So. Right.
Okay. And I mean, are we always looking for it? It looked like it almost had an oval shape as opposed to a regular shape. It was fairly malformed on the examples that we saw there. Let me see. Adam, I mean, have you any views on the actual detection of head and pillow defects?
On some factory floors, one of the ways that I've seen people do is they'll actually wire the board up for functional testing, and they'll apply pressure to the top of a BGA component and see intermittent connections. Right. So that's another way to do it without having to destruct it if you have a hunch. So.
Right. Okay. All right. Well, thank you for these examples, Piotr. What is the difference between head and pillow and head on pillow? I mean, there's two different defects, aren't they? Who's going to go first with that?
We don't really distinguish. It's just nomenclature, basically. Head on pillow, head and pillow is the same defect by our definition. So
is it?
No.
Okay.
Yeah, same with us. So I mean, it all depends. It makes more logical sense because you put your head on a pillow as opposed to inside a pillow. So I mean, if you could just think of it that way, that's kind of, there's been many a conversation about the in or on portion, but for all it's worth, it's pretty much the same thing.
I just wondered whether, the one meant that the ball was slightly collapsed or not, and if there was a difference between head in and head on the pillow. But okay, fair enough. So let's look at what are the primary causes of head and pillow defects. Piotr, do you want to kick us off with that?
Sure. So basically, there are many reasons for head and pillow. Some of them has a bigger impact or bigger factor, or smaller. I guess there are two most important causes, and one of them is the package warpage. I already maybe introduced a bit in my presentation. So basically, package has a tendency to warp a bit. Inside the Reflow oven, you do the different coefficient of thermal expansion in materials that are used to build the component itself, and the PCB. Second cause, it's a solder phase contamination or oxidation, and of course, this is preventing from having good from the wet properly, have the wetting properly between the BGA ball and between the solder phase printed on the PCBs. Of course, there are some smaller issues like process issues that maybe can be controlled by the manufacturer, like the printing process. Of course, reflow is very important, or even pick and place. And also more, I think, related to like a supply, like solder paste quality or components quality.
Kevin, anything to add on that?
No, I guess from our standpoint, if we strictly talk about causation, it's thermomechanical. I mean, you're talking about warpage that's driven by heat. So you're basically getting separation between the package and the PCB. And this is really what we consider the cause. There are a lot of overlying factors. You can do paste modifications. In fact, you can use a lower temperature solder paste to have a lower reflow temperature, which is going to minimize that warpage as well. But in general, I mean, everything points back to it's a warpage induced defect. So there's a lot of overlying factors. There's a lot of band-aids that we can apply. There's a lot of optimization, I think, that can take place. But again, just going back to causation, we're really chasing CTE mismatch of materials between the package and the PCB.
That's true. I mean, I see a comment in here from one of our audience, Matthew Gruber, who's saying, I see a reflow issue resulting in a lack of homogeneous melting of the paste and the ball. So it could be a materials mismatch slightly. Could that be a contributory factor?
Well, I think from the standpoint, at first you have to have separation. If everything was uniform, then you're making contact the whole time between the BGA ball and the solder paste deposit. And from that standpoint, you're relying on the flux activity to coalesce between the BGA ball and the solder paste deposit. Again, the problem really, or the challenges increase when you get separation. And so it can really be driven then, I guess, two different paths. One can be maybe you cool down before the warpage relaxes, so to speak, or unwarps back to the board. And if you get cooling down, then you get solidification. And then you don't coalesce between the BGA and the solder paste deposit. The other aspect of it is if you actually consume up the flux activation of the paste or the flux, and maybe you have a limited oxidation barrier left on that can attack, basically the oxidation of the BGA ball. So,
right, okay. So, Adam, I mean, our head and pillow defects limited to BGAs. I mean, do you get them in other devices in any way, or is
I haven't had it described as a head and pillow, but it's primarily a BGA defect for sure.
Yeah. Okay.
Or any ball device.
Any ball device.
Normally large in surface area, which causes the warpage.
Yeah. Okay. Let's see. What about the sphere size? Does that have any influence on the defect? Does the sphere size, does it contribute to the defect, or does it help it?
I think it's a contributing factor because the smaller the sphere size, the smaller the aperture, and the less paste you would put down on the PCB, and the greater chance of oxidation or graping that would happen on smaller deposits in a conventional reflow environment. So I don't think it's a direct cause, but if you to what Kevin mentioned about the oxidation barrier, if you don't have a paste that has an adequate oxidation barrier, then you could get graping, non-coalescence, and resulting in a head and pillow.
Absolutely. Okay. So I think you probably answered my next question, which is are smaller devices more likely, more prone to warpage? I would have thought larger ones are actually.
Yeah, definitely. But so to add on to what Kevin mentioned about the head and pillow defect, the real cause, in my opinion, is more of the oxidation, less the warpage. So let's say if you have a BGA that has not been stored correctly for a very long time, and you have a really thick oxide layer, and your paste can't go there, and it doesn't warp at all, you can still see the head and pillow defect. So you have to solve the oxidation problem even on top of the warpage problem.
That's interesting. So the oxidation is a bigger contributor than the warpage, is what you're saying.
Warpage will definitely put it over the edge for sure,
Mm-hmm.
especially with today's modern chemistries. But yeah, oxidation is, in my opinion, the root cause.
Right. Okay. So let me see. Let's jump back to Kevin for a moment here. What's the difference between head and pillow and non-wet open defects?
Basically, with a non-wet open, you don't have any solder left on the pad, and that could be due to the solderable finish itself. It could be due to an interaction between the paste. Maybe the flux isn't aggressive enough to wet the pad, but basically the paste deposit ends up wetting preferentially to the BGA ball and is pulled up basically by capillary action, kind of sucked up to the ball and doesn't wet the pad at all. So.
Mm-hmm. Okay. Anybody get anything to add on that, on the comparison between these two defects?
I've seen it happen more with dipped devices.
Okay, more prevalent in dip devices. Why is that?
Well, if you're dipping into solder paste, the ball is the first thing that make contact, as opposed to a printing process, which is on the board level first. So I've seen more non-wet opens on dippable devices for that reason.
Okay.
Just add one comment here. So basically, I will just point out again for inspection. This is very important. So I think what is when we have a head and pillow, the connection is enough to have, like, let's say, electrical integrity, but there is not enough mechanical strength. So it will very often pass your ICP. So this is another thing why it's important and difficult to find. If you have, of course, if you have an open web, then it will fail your ICP because there is no any contact. If you have a head and pillow, it might be a contact, but of course, with some temperature or any stress, it might break. So even with the ICP test, it can pass, and those are, I think, also different.
Okay, that's interesting, Piotr. So does reflow temperature have an effect on it then? Piotr,
Yeah.
Does the reflow temperature have an effect on the defect?
Yes, I think actually, if we are looking on the process, the reflow has the biggest impact, and it can improve or reduce the head and pillow problem. Higher temperature, longer exposure for the temperature can increase the risk of head and pillow. So good adjustment of, I would say, complete reflow process. So this including ramp rate or peak temperature or even cool down time, it might have a good effect. So I guess it's important here to point to the component data sheet to adjust the profile correctly.
Yeah, or as Kevin said earlier, if you went towards a low temperature sorter, then maybe that might be a bit more reliable process. Okay, let me see. Kevin, how important is the pick and place accuracy?
I guess it depends on device or package size. For smaller components, I think it's maybe not as important since you're more than likely to self-center. But as these devices get larger, and along with them being larger, you have decreasing pitch. I think it can be quite a bit more critical because the larger the package, it's going to be more challenging to self-center. So, which then I guess goes back and overlaps with what somebody already else said about the solder paste quantity. If you're not aligned properly, it's also going to impact your effective solder paste quantity as far as the flux activation and exposure to the BGA ball. So,
right, okay. Adam, have you anything to add to that?
Not really. I mean, Kevin pretty much covered everything with that.
Okay.
Yeah.
All right. Okay. What steps should we take to avoid, the occurrence of head and pillow defects? What prevention can we take?
I can take the first crack at that one. I think talking with your solder supplier and your component supplier is the first step. Understanding how your component warps, if it, smiles or if it frowns, and at what temperatures it starts to do that. And then essentially then going to the reflow profile and making sure that that matches the appropriate recommendation from your solder supplier to reduce the defect as much as possible.
Right. What makes the difference between whether it smiles or whether it frowns? I mean, what's going on there?
So that, I mean, it's different stresses.
Mm-hmm.
So I mean, if it smiles, right, your defect's going to be on the perimeter balls.
Okay.
Whereas if it frowns, it's more in the center. If it's on the perimeter, you may be able to see it with just your eye or a microscope. But if it's on the perimeter, you can also fix that with an aperture modification and potentially put more paste down in those locations to get rid of that.
Yeah. Yeah. Okay. Good point. Okay. Anybody else want to take a stab at that question? What steps should we take to avoid the occurrence of head and pillow defects?
Yeah, I would just say again, if there's the opportunity, it's going to be very application dependent, but consider a lower temperature alloy or product. And that's going to be coupled together with the package and the PCB design. Obviously, there's a lot of overlap there. So, it's as far as seeing that there's the opportunity for that lower temperature product. But yeah, going back to exactly what Adam mentioned, talking to the suppliers. I mean, it's a well spoken of topic, I think, from the package side, maybe more than the PCB side, about minimizing warpage. So definitely they're part of the discussion as well. And the other thing is maybe a nitrogen atmosphere can help minimize it, and that addresses or helps address the oxidation issue that Adam elaborated on earlier. And maybe in some cases where you might have the opportunity to selectively increase the paste amount. Going back to the description of the frowning versus smiling, you can selectively increase the paste by stencil design, and it can help compensate for some of that warpage as well. So,
okay, that's a good idea. Anything to add to that, Piotr?
Those are, of course, those are very good examples. So basically, of course, improve the process, improve the materials. But I think what is also important here again is the inspection. So basically, while we are modifying our process, I think the key is to have a good, complete inspection. X-ray, of course, for the end product, but also during the manufacturing. Good SPI, pre and post reflow AOI can provide a lot of data where we can apply those all actions that you guys already mentioned. And of course, collecting this data and have a tool to analyze it, to collect things in one place, analyze it. A lot of information and a lot of indicators. Which of those actions shall we apply to improve our process and to reduce head and pillow?
Okay, yeah, of course. Inspection is critical. Okay, we've got a couple of questions coming in from our audience, so I'm going to turn to them. I've got one from William Hope, which I'll give to you, Adam, first of all. Some high reliability solders have lower melting points in the region of 205 degrees C compared to SAC alloys, which is around about 221 degrees C. If one profile the oven to reflow the high reliability solder with a peak temperature of around 225 or 230 degrees C, can this cause head and pillow? And that kind of feeds in from the second question, which is that most of these solder balls that you get are SAC 305. So if you're using a different paste on the board, could you have a mismatch there?
Yeah, definitely. If you're not collapsing the ball and making a homogeneous joint, then yeah, you could potentially have a mismatch. But from a reliability perspective, you really have to take into account the thermal excursions or thermal cycling requirements that your device entails. There are certain white goods that only require like a 0 to 100 degrees C thermal cycle for X number of cycles, whereas automotive goes -40 to 150. So there's such a wide range of that. So by picking a different alloy, whether it's high reliability or low temp, you really have to consider the failure mechanisms associated with that. And the resulting intermetallic layer, let's say if you're going with a lower temp solder, based on the bulk, because that is where the propensity for a crack could occur, is that interface.
Right. So Kevin, I mean, why are most of these BGAs all SAC 305? Why don't you make them with other alloys?
I mean,
Yeah.
it's more history than anything. Correct. I mean, everything used to be tin lead. So,
Right.
and then when the industry shifted to lead free, you had, I mean, I've seen solder, they're all SAC based, right? Whether they're 305, 105, low silver. I'm seeing a lot of SAC Q recently in BGA metallizations. So it's really about compatibility and resulting reliability of devices. Matching alloys are more friendly to each other.
Okay. Okay, so Kevin, we'll give the last word to you on this topic of the mismatch or potential mismatch between using SAC 305 and different alloys. Do you have a view on it?
Yeah, I mean, actually, there are some cases to where you can have mixed alloys and even end up with very, very good performing results. And what you have is a heterogeneous solder joint, basically. And we've seen very good results from that, actually, and how the stress is applied to the package. So there can be actually benefits in that case. But it really goes back to understanding the end use application, as well as what type of components, what type of PCB. So I think most people agree there's not really one size fits all for the best choice for every application. And as far as SAC 305, maybe the end use for the package size, I think it is the way it's been. And maybe it's not the best way going forward. So again, so it goes back to knowing the process better, knowing where you might have latitude to make some changes. So.
Yeah, exactly. I mean, if you're going to have heterogeneous integration coming into the board level, then you're going to have to sort of get a bit more, matched alloys working there for sure. Okay, well, I think we've pretty much talked through most of the subject. We've covered a lot of areas. I think the oxidation barrier, as you mentioned, Kevin, is critical, and maybe putting a little bit extra paste down around some of these peripheral balls can be helpful too if you detected some warpage. So I want to thank you for your input today, guys. I don't think if we've got any more questions coming from the audience. No, I don't think so. So okay, so let me just say a very big thank you to Adam Murling from Indium Corporation, Kevin Martin from MacDermid Alpha, and Piotr Swietoniowski from OMRON. Thank you, gentlemen, and thank you to our audience for watching us today.
Co-Young is leading a smart revolution that will change the world of electronics manufacturing. Based on our pioneering True 3D measurement-based inspection technology, we revolutionized the solder paste inspection market to such great lengths that 1 in 2 SPIs sold today is from Co-Young. Building our SPI technology, we expanded to automated optical inspection, also known as AOI. Every year, we introduce new award-winning innovations and have proudly earned the respect from thousands of customers across diverse industries. Aside from our R&D center in Korea, we have research facilities focused on artificial intelligence and deep learning across the world to help us further develop proprietary AI technologies for your challenges. With our global network of sales and service centers, we aim to respond quickly to your needs and to deliver the highest level of customer satisfaction.
Global SMT and Packaging opens the windows of the world to bring you the latest news and technologies from Munich, from Bangalore, from Shanghai, from San Diego.